All right, so I'm going to pick up with our next key discussion. All right. To do that, I want to begin with remembering kind of what we call the 5 key properties of a good control system. All right, so the 5 things that we laid out is we said we want a good command following. Essentially, what that means for us is that the steady state output should be approximately whatever the steady state input is. In other words, whatever I tell the system to do, which is the steady state input, better be what it does in steady state. In steady state, I better have good disturbance rejection. So any disturbances that I have that are trying to change the output better not have any impact. There should be good noise rejection. So any noise I've got doesn't affect the output. Low parameter sensitivity, meaning that if the parameters of the system, if the model of the system changes, that doesn't affect the output. And I also want that thing to be stable. Now, so far, we've talked about the first 4 of these. All right, maybe not so much about the noise, but I've talked about these. All right, and these we said were all really kind of, in general, these are steady state issues. Okay, this guy here is different, stability. This is a transient issue. Now, I want to kind of understand that, and just figure out what that means. Okay, why do we start talking about stability when we start talking about control systems? Right? We need to understand, kind of where that comes from. So what I drew out here is a pretty basic and kind of silly control system, all right, where my plant, I'll call it, is an RC circuit. So this guy right here is my plant. Now we'll see why I use that plant. I like that plant. The RC circuit's very simple, and it has simple, what we call first order dynamics. Okay, so as I kind of discussed previously, what that means when I talk about orders of systems, what I say is that if I can identify in my system, so in my plant, if I can identify one energy storage element, then I have a first order system. If in my system I can identify 2 energy storage elements, I have a second order system, so on and so forth. All right. Now, we talk a lot about first and second order systems. Why? Okay, that's what we want to understand a little bit. Now, why do I choose the RC circuit? It's a first order system, and many, many, many systems are first order systems. So pretty soon we'll start talking about DC motors in this class. That's one of the, and we don't really just talk about DC motors, I could talk about AC motors too, but those systems tend to be well represented by first order systems. All right, and so what we'll see is we'll design a control system with that DC motor, and it's going to look a lot like this picture right here. The only thing that'll be different is I'll replace the plant with what the motor looks like. All right, so this is a basic control system, and I've got a couple of elements. So what I want to do is I want to make a model for this actual circuit as a control system. All right, so I'm going to start over here with my VN. This guy is basically I would represent him as my R of S, okay? In other words, I could say, in this case, R of S is the Laplace transform of Vn of t, okay? That's my overall input. Now, if I look at this guy right here, right, this is a subtractor. Okay, go back to your basic circuit analysis, and what you find in basic circuit analysis is if R, and R are all equal to each other, this guy here will give me the difference of Vn minus whatever's right here. So in other words, I can model that subtractor, I can model that guy like that, okay? This is a model for my subtractor. Now, this guy right here, okay, has a transfer function that you've seen before. Basically, from output to input, this guy has a gain that is, if you solve for it, R1 plus R2 over R2, or Sometimes we write it like that. Okay. In this case, I'm going to model that guy as Kp. Okay. So the output of my subtractor goes into that block, Kp. Okay. Now my plant from output to input, or sorry, from input to output, so meaning from this voltage to, so from the voltage here, the voltage here, to the voltage across the capacitor, this guy is just 1 over S tau plus 1. And then my V out here, via Laplace transform, I can say is my C of S. And then I take that voltage and put it through a follower. So this guy here has a transfer function from his input to his output of 1. Right, so I leave myself much space here, but draw that like this. All right, so that's my basic model for that system. Okay, now what I want to do is I want to analyze this guy for a second. All right, so let's analyze that. So let's go. Let's go here. Okay, so what we had was a model R of S minus plus Kp one over S tau plus 1, and then I had unity feedback. Okay, so if I want to get my closed loop transfer function C of S over R of S, I use my Black's formula to say that that's Kp 1 over tau S plus 1. So Kp times 1 over tau S plus 1 over 1 plus that. So Kp over 1 over tau S plus 1. Now, typically with these transfer functions, I want to get these guys in what we call a proper form, which means that what I want is polynomial of S on top and bottom, right? That means that I multiply top and bottom by tau S plus 1, okay? Like that. I multiply everything through like that. What that becomes, Kp over tau S plus 1 plus Kp, like that, okay? Now I'm going to rewrite that guy. I'm going to basically, what I'm going to do is I'm going to factor out a 1 plus Kp on the bottom, okay? So that's going to make this tau over Kp plus 1 S plus 1, right? You guys can stare at that later to see how that makes sense. So that turns this guy into Kp over Kp plus 1, 1 over tau S plus 1. Oops. Okay. All right, why did I go through that? Okay, so I took that system that I showed, I modeled it, okay, and then I said, okay, what I've done is I've created this system, okay? So I want to compare something for a second. If I look at my original RC circuit, my original RC circuit had a transfer function. G of S is 1 over tau S plus 1. Now we're going to talk a lot more about this through this lecture, but if I talk about a system, G of S, that has this first order transfer function, then if I have a step input to that g of s, what I get is an exponential output that settles at some point. Okay. The rise of this guy is controlled by tau, the time constant. Okay. What's important and why I wanted to talk about this is if I look at this RC circuit, there is nothing about that RC circuit that is unstable. If I put any input into that RC circuit, I'm going to get a nice stable output, right? There's nothing about an RC circuit that is unstable. If you look at what I have done here, by taking this RC circuit, so taking, in other words, more generally, a system with first order dynamics, if I take that system and I put it into a control loop like I have right here, what I've done is I've basically taken this guy here and I've created a new first order system with ultimately a new pole. You look at this guy, Kp over Kp plus 1. This guy is still first order, but this guy has a different time constant. Okay. In fact, this guy's time constant, if Kp is bigger than 1, right, then effectively what's going to happen is this guy has a smaller time constant. Okay. So which is typically what we do. So if Kp is greater than 1, in other words, if this guy has a gain block, Kp is greater than 1, tau prime is going to be smaller than tau. Ultimately, what that means is this system is faster than the original. All right. In other words, this guy's still like an RC circuit, right? I took an RC circuit, put it into this control loop. It's still an RC circuit. But effectively what I've done is I have changed the transient response of that RC circuit. Okay? So the original RC circuit had a time constant tau. He responded just so fast based on that tau. Once I'm in the control system, this guy responds faster. Okay? Now that's not a big deal for this first order system. But the key point is this. By placing this system in a control loop, I've changed the transient response. In this case, I've made it faster. What that means is that when I'm using control, by placing a stable system, an otherwise stable system, into a control loop, I'm changing the transient response. And thus, I'm potentially flirting with the possibility that I took a stable system and made it unstable. By changing the transient response, I make it possible to be unstable. Okay? The transient response of a system is directly related to the stability of the system. And so if I begin to manipulate that transient response, like I did here, okay? So I ultimately made another first order system. So I started with a first order system, putting it in a control loop, basically converted to a new first order system that was faster. I'm changing the way this system behaves. Fundamentally, I'm changing its transient response, and by changing its transient response, I'm potentially flirting with the possibility that I can make an otherwise stable system like this RC circuit become unstable. Okay? All right? That's the reason why we spend a lot of time talking about stability. When I look at control systems, when I look at the idea of using a control system, I'm manipulating the transient response of that system. All right. So, with that kind of key idea in place, okay, it's kind of, again, kind of an important picture. We'll talk about this same guy again in the context of our motor, but we'll replace this plant, okay, we'll replace that with a motor instead. All right, now what I want to do is I want to talk a little bit about first order systems, just from a more general perspective, okay? So we saw one just there. We're going to talk about maybe systems, kind of from sort of a real general sort of concept here for a second. Okay. So here's a system, any system, G of S has an input R of S and an output C of S. The important thing to remember, and we're going to talk more about this next time, this is a model, okay? Models are useful for design. In other words, what I want is a mathematical model that captures the dynamics of that system. And if I've captured the dynamics of that system, in other words, I've captured how it responds in some way to a certain set of inputs, I've captured the information I need to know about the transient response. What I know is that in my control system, I can potentially manipulate that transient response. I want a model that expresses that transient response so I can understand how I'm manipulating it, okay? So this guy's a model for a real system like this guy, right? So here, up the top, I have a model. So all the things that you've learned up till now in other courses have basically prepared you to build this model. What we want to do in this class is begin to understand how we analyze that model to create the control system that we want. Okay? So if I'm looking at this sort of general perspective, right? This guy's a model. Now, in general, what we're sort of interested in is what happens in the time domain. Okay? The time domain is the real world. So it's an important thing. The time domain is basically the real world, right? It's the world that we live in and experience on a regular basis, right? So if I have, for instance, a step input would correspond to, well, if this V in here was a function generator and I turned that function generator on, that would be a step input, okay? In the real world, I would observe a step input. In the frequency domain, that would mean that this guy is represented by 1 over S. 1 over S doesn't exist in the real world, okay? The step input does. I could go to an oscilloscope and see that step input. All right, so in general, when I'm looking at any system, right, what I'm looking for is some way to get from R of t, right, to C of t. In other words, I want to see what happens in the real world. Well, the way to get from R of t to C of t is differential equation, okay, which we know to be sort of a painful process. So we move everything over to the Laplace domain because basically it makes the math simpler. So we can convert that differential equation to the Laplace domain to make everything simple. Okay? Now, we're going to use that a little bit here. Okay? So in general, if I look at this G of S, right, I made a couple of points here previously, and I want to kind of highlight those. This G of S is my system model. System model. Okay? And this system has poles and it has zeros. Okay? Zeros are where G of S equals 0. Poles are where G of S is magnitude at least approaches infinity. Okay? So, as an example, I'm going to look at this guy, who's the first order system. Okay? S plus 2 over S plus 5. Okay? Now you guys should remember, this guy has one pole and one zero. So his 0 is located at S equals minus 2, okay, which is where, because remember G of minus 2 is equal to 0. And he has a pole at S equal to minus 5. G t of minus 5 approaches infinity. Okay, so okay, just basic stuff, okay, for us to remember. But one thing that I want to kind of bear in mind here, this is kind of the important piece for me, is that the number of poles is always equal to the number of energy storage elements, okay, which is also always equal to the number of exponentials in transient response. Okay, let's keep that in mind. All right, the number of poles is always equal to the number of energy storage elements, and it's always equal to the number of exponentials in the transient response. All right, just kind of a general concept that I want to kind of look at. All right, so if I have this g of s equal to s plus 2, s plus 5, let's say what I want to do is I want to look at the step response of this system. Okay, so if I'm talking about the step response of the system, so let's do step response. Okay, so let's say I've got, draw that picture again. Okay, this time I'll just sort of write it in there, s plus 2 or s plus 5. Say I want to figure out what c of s is. And not only that, really what I want to figure out is I want to know the step response. So in other words, what I want to know is what is c of t when r of t equals the unit step, or what we say is u of t. Okay. Okay. So that means that r of s is 1 over s. Okay. So what that says is in this case, my input has a pole. In other words, the input has a value of s that makes it go to infinity, right? So my input has a pole, right? So I've got one pole in my input, got one pole in my transfer function, okay? So you guys should know that if I have a transfer function like this, I can say that c of s equals g of s, r of s, right? And if I use Laplace transforms and then apply the inverse Laplace transform, that provides a much simpler way for me typically to be able to determine what c of t is, okay? So let's play that out. Okay, so I substitute in what g of s is, substitute in what r of s is, right? So now I have the Laplace transform of the output, and I need to inverse Laplace transform that. Okay, so you guys learned that if I wanted to compute an inverse Laplace transform, I use the method of partial fractions, okay? Which basically says for a system like this, what I have is a over s plus b over s plus 5, okay? And the whole goal of that partial fraction expansion idea is to figure out what is a and what is b, okay? Now, if I go through that process here, what I will find is that a is equal to 2/5 and b is equal to 3/5. I'm not going to go through that. You should be able to figure out how to do that. All right. What that ultimately means is that as I go through the inverse Laplace, as I go through the inverse Laplace, I get that c of t, basically, what I do is I go through an identification process and I say, well, this thing right here is the Laplace transform of a step function. This guy is the Laplace transform of a decaying exponential. So what I get is 2/5 u of t plus 3/5 e to the minus 5t, like that. Okay, that's what I ultimately determine, all right, to be the inverse Laplace transform of this guy. Were I to plot that thing, okay, you guys should know that this is a unit step times 2/5. Whereas the height of this is 2/5. Okay. And I know that this guy is a decaying exponential. So he will look like this. Okay. Whereas maximum value here is 3/5. And I should be careful. This is actually a decaying exponential times u of t. All right. His peak value would be 3/5, starting at time t equal to 0, and he would decay. The combination of these two things ultimately looks like that. Okay. All right. If I add the two of them together. Okay. And you guys can work that out. It's not a hard thing to do. All right. Let's kind of visually picture that. That's kind of what I wanted to do. All right. So I have 1 over s is my input. Goes into the transfer function. Gives me a c of s. Combined. All right. All right. So if I look at this, 1 over s is my. So 1 over s here is my input. Got my transfer function. So what I've shown here, this is the sort of the pole 0 plot. For g of s, for my system. Okay? So it's got a 0 at -2, a pole at -5. Okay? Now this input, I said, has a pole. So I can express it in the s-plane with the pole there at the origin. Then the system, I can basically look at these two things independently. So I've got a 0 and a pole. Okay? So what I see ultimately is I always get, once I look at the transform of the output, okay, like we did previously, the transform of the output always has within it a term related to any poles in the input and a term related to any poles in the system. Okay? So in other words, C of S has terms from poles of input plus terms from system pole. Okay, so I have terms from the pole of the input plus terms from the system poles. Okay, ultimately, this is the key piece, right? The terms from the poles of the input give me the forced response, or what I sometimes call the steady state response. Okay, the poles of the system give me the natural response, or what I sometimes call the transient response. Okay, so poles of the input give me the steady state response, So in other words, what happens once the transients are over? The system poles give me the transient response. Okay. So the transient response of the system is particularly important. Okay. Why? Because if my system is unstable, right, the only thing that can make that system unstable is if the system poles are such that the system is unstable. Okay. And so this idea is kind of critical to me. Okay. So here's the way I sort of picture this, right? I can always, via partial fraction expansion, I can always ultimately break up that G of S piece into, if I have n poles, so for n poles, I get n terms in C of S. Okay, basically meaning n exponentials in my output. Okay, plus I get terms due to the poles of R of S. So what that means is, if my R of S, if my input is a bounded input, okay, these poles also give rise to exponentials. But as long as I provide a stable input, this guy, these exponentials never cause an issue. As if I have so that stability of the system is entirely controlled by the poles of the system. Okay? Key takeaway, stability of the system is always controlled by the poles of the system. Okay? If I look and try to perform the inverse Laplace transform of these guys, as long as I have no repeated poles, okay? No repeated poles, meaning that P1 is equal to P2, which is really hard in real life anyway. All right, it's really, really hard to achieve. Okay, as long as I have no repeated poles, essentially what I have is either these guys look like as I've written this guy has an inverse Laplace transform that's an exponential. This guy has an inverse Laplace transform that's an exponential. So if I were to write the sort of the time domain piece of this guy, I would have k1 e to the negative p1 t plus k2 e to the negative p2 t, so on and so forth. Now, in some cases, right, I get these decaying exponentials. Okay, I get decaying exponentials if and only if P1, if my P sub I guess P sub I is real. If P sub I is real, I get decaying exponential. Now, if it's the case that P sub I is complex, if P sub I is complex, ultimately P sub I has a partner, a complex conjugate, somewhere else in this thing. So in other words, if P1 was complex, P2 would also be complex, and he would be the complex conjugate. So two of these give me a decaying sine wave, all right? Or really a decaying complex exponential, okay? Bottom line to all of this is that the poles control the transient response. And that transient response consists of, in general, decaying exponentials or decaying complex exponentials, meaning decaying sine waves. Okay? Generally speaking, if I look at this guy by himself, if I look at any one of these terms by themselves, what just so happens that this guy looks like a first order system by himself. This guy looks like a first order system by himself. This guy looks like a first order system by himself. Only if my poles are complex do I really need to think about things as being second order systems. So what we're ultimately going to see is, in general, depending on what my poles are, I can think of my systems either as being first order systems or second order systems. So if all my poles are real, I can probably think of that system hopefully as first order. If all my poles are complex, I can probably think of that thing as second order. The transient response of the system, okay? If my system is stable, so if I have a stable system, I know that my transient response, so for this system to be stable, sorry, this guy's really hard to write with in PowerPoint. Transient response goes to 0 as t goes to infinity. In other words, the transient response goes away. For the transient response to go away, because that transient response consists of decaying exponentials, it must be the case that all of these p sub I, the real parts of them, must be less than 0. Right? The only way for these things to go away is if the p sub I are less than 0 and these are decaying exponentials. All right? So to have a stable system, all the real parts of my poles must be negative, meaning all my poles are in the what we call the left half of the complex plane, so that my transient response goes away. All right, so all I wanted to kind of review here today is I go back all the way to the picture I said here. I wanted to talk about the stability. Okay, stability is related to the transient response. Okay, if my transient response does not decay, in other words, it doesn't go away after I wait long enough, that system is unstable. Okay, that system is unstable. If the transient response doesn't disappear eventually, the system is unstable. Okay, why we talk about this in the context of control, like I said, I can take a very stable system like this, and by putting it in a feedback loop, I ultimately take this first order system and convert it into a new first order system with a new pole. Depending on what my controller is, so in this case I get a very simple controller, but let's say that controller also had a pole in it. Now my system has become a second order system, and I have introduced a new pole, and I move this pole. So I'm completely changing the transient response of this overall system when I do that, okay? Because I'm doing that, because control systems requires me to modify the system model, I am modifying its transient response and hence moving its poles around and potentially making it such that my poles no longer have real parts to them, meaning that it's possible for my transient response to not go to 0 anymore, and thus for my system to become unstable. That is the crux of a lot of the stability analysis that we'll do. By making a control system, we can make an inherently stable system become unstable because we're modifying its transient response. Okay? And because it is the poles of the system, that's the other thing, because it is the poles of the system that control the transient response. The poles of the input have nothing to do, right? This is a key piece. The poles of the input give us the steady state response. The poles of the system give us the transient response, okay? Because of that, it's really important for me to spend time understanding that transient response. I can modify that transient response when I modify the system, which is what we do in controls. And I could potentially modify that a bad way. Okay, so I want to spend a little bit of time here kind of understanding some important stuff about a particular class of systems. Okay, so enough about sort of this general concept, right? The notion of stability is controlled by the system poles, and in controls, we modify the locations of those system poles. So I can take what was a stable system, and I can make it unstable. I can also, as we'll see, and one of the things that you're going to be playing with in the lab, is I can take a system that is naturally unstable and make it stable. Okay, I can modify an unstable system and make it stable. All right, so we'll talk more about that, but that's one of the key things we do is we modify transient responses. Okay, so what I want to do for the rest of the time here is I want to look at sort of a common class of systems, the first order system. Okay, and that first order system has a transfer function that looks like what I've shown here. All right, this is what I call, I guess, the canonical form. All right, the canonical form. More generally, this guy starts to get really slow when I write on PowerPoint. More generally, what I have is some constant over tau s plus 1. All right. In other words, my canonical form, basically what it means is this guy has no, what I call DC gain. In other words, when s equals 0, right? When s equals 0, the gain of this guy is 1. When s equals 0, the gain of this guy is a. All right. In general, so both of these are first order systems. This is kind of a more general sort of first order system. Okay. This canonical form I use because it's just a little bit easier to play around with. I don't have these extra terms like this a factor to worry about. All right, but just so we understand, this is sort of the more general form. All right. Now again, what I've said is this is a model. Right. This guy could be a model, as I said, for. Oh, it's getting even slower. He's a model for an RC circuit. Okay, this RC circuit has a transfer function 1 over tau s plus 1. Okay, typically when I'm looking at this guy, there's a couple of ways of trying to figure out what C of t is. So one thing I could do is I could look at the the differential equation, right? And what I would find for that differential equation is my input R of t is equal to my output C of t plus tau times the rate of change of C. Okay, like that. And I could solve that differential equation if I know what R is to figure out what C is. Like I said, that's the most general way of looking at this. But nobody ever really wants to solve that problem. So we're not gonna, we're not gonna spend a whole lot of time, on that guy. So what I would typically want to do is say, okay, well, for certain types of inputs, what I can use is the Laplace transform and do the inverse Laplace transform to figure this out. So just something to bear in mind. Yikes. Let me do this. I think that might speed it up. Okay. So, or not. Let's do this. Be faster over here. Okay. If I have